Okay, in this lecture series, we're going to go ahead and look at two-dimensional problems. And the reason we want to go into two-dimensional problems is that most of the world is actually in 3D. And so we've already talked about one dimension. Now we're going to go into two. If you're going to go into engineering, you'll go into three-dimensional problems. I'm not going to do that for this course. Okay, so let's go ahead and look at example one. We have a block that has a mass of capital M. It's being pushed across the table with a force on block by person. We're going to solve for the normal force and the applied force in terms of the mass, the acceleration due to gravity, the acceleration of the block, and the coefficient of friction. They didn't explicitly tell us that whether we're in equilibrium or not, and they didn't tell us whether there was friction or not. But notice what they're asking us to solve for in terms of, here's A, the acceleration, so that tells me I'm going to be accelerating. And here's mu sub k, which tells me I have friction. This is your kinetic frictional force coefficient. Okay, so let's go ahead and start by drawing the motion diagram. I've already done that for you, so you'll just need to copy it down. We are going to be increasing our velocity. I've increased it by 5 millimeters for each time interval, and I've drawn the acceleration in the same direction as the block's motion. So go ahead and pause the video now and go ahead and draw your motion diagram. Okay, so now we're ready to ask the questions. What's physically touching? What's acting at a distance? So what's physically touching the block? We have the table. Anything else? The person. That's right. Is the table touching by rubbing, supporting, or both? It's actually doing both. So we're going to count that as two forces because we got a rubbing force and we got a support force. So now we're at 3. So what's acting at a distance? Earth. So that gives us 4 forces. Are we in equilibrium? No, we're not. Okay, so what we're going to do is we're going to go ahead and draw our forces. I'm going to start with the dot. Okay, so this is going to be force on block by table. This is force on block by earth. And now I need to draw my applied force and my frictional force. Because I'm accelerating to the right, I'm going to make that longer than the one to the left. Now, would this change 5 seconds later? No, the lengths of these forces do not change throughout the problem. Okay, remember that we use a lowercase f for friction. So that's force on block by table. And I'm going to label this. This is your normal force. This is your support force. This is your weight. This is your friction. And this is going to be your applied force. Force on block by person. Okay, so those are the forces that are acting on the block. Okay, so now we're ready to sum the forces. Here's the thing though, can we add these forces together numerically? No, we can't. We have some going east and west and we have some going north and south. We can only add I hats with I hats and j hats with j hats. That means that we have to separate the equation just like we did for projectile motion. Okay, so here I'm going to do the sum of the forces in the x direction is equal to max. And over here I'm going to do the sum of the forces in y is equal to may. Okay, and I also am going to fold my paper hot dog so that I can keep everything of x on this side, everything of y on this side. Okay, so the first thing I'm going to do is I'm going to just go ahead and do x first. So let's go ahead and add up all the forces on our free body diagram. I have friction and I have the applied force. So I have lowercase f on block by table plus capital F on block by person, and that's equal to ma sub x. Okay, am I accelerating in the x direction? Yes, I am. Newton's first law. Okay, now I'm going to substitute in magnitude and direction. Now, this is where you substitute in the formula as well. Remember that the frictional force is equal to the coefficient of friction times the magnitude of the normal force, okay, plus its direction. So this is where it gets a little tricky. Your lowercase f, which represents friction, this is going to be replaced with mu times capital F on block by table. Okay, so watch this. This is friction. Then we have minus, because it's going to the left, minus mu sub k, because we're moving, times the magnitude on block by table. Notice the absolute value bars. That tells me that I'm not going to put the j hat in here for this direction. Magnitude. So this is the magnitude of the normal force. And that's in the I hat direction. Now you may be saying, negative I hat direction. You may be saying, whoa, 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 whoa. How did friction become normal force? It didn't. This entire statement is the frictional force. Okay? Mu times the magnitude of the normal force is equal to the magnitude of the frictional force. Negative I hat is the direction. Okay? Take the magnitude of the normal force, multiply it by the coefficient of friction, and that gives you the frictional force, magnitude. Okay? You have to be able to keep the lowercase f and the capital F straight. Okay? So now we're going to add force on block by person. And that's going in the I hat direction. And that's going to be equal to ma I hat. And I'm going to substitute this in with the capital M, since I've already substituted in the A from the problem. Okay, we're going to cross out our unit vectors. So let me do that. Cross out our unit vectors. And now we're going to solve for the unknown. Well, do we have mu? Yes. Do we have the normal force magnitude? No. Do I have force on block by person? No, that's what I'm looking for. Do I have MA? Yes. So it turns out I have two unknowns in this equation. So if I have two unknowns, how many equations do I need? Two. That's right. So what I'm going to do is, instead of solving for anything here, I'm going to leave this be for right now because I need another equation. So I'm going to go ahead over to the y direction and see if we can get another equation there. Okay, so adding up the forces acting in the y direction, I have force on block by table plus force on block by earth, and that's equal to ma sub y. Am I accelerating in the vertical direction? Look at your free body diagram. Look at your motion diagram. No, we're not. So I'm going to go ahead and set this equal to 0, Newton's first law. Okay? So now we're going to go ahead and substitute in magnitude and direction. I have force on block by table, j hat, minus mg j hat is equal to 0 j hat. Okay, I can cross out my unit vectors. I have m and I have g, so I can go ahead and solve for the magnitude of the normal force. So force on block by table is equal to mg. Now, I was asked to solve for the normal force, so I can go ahead and write this in vector form. Force on block by table is equal to mg j hat. And why is it not negative? Because this force is going up. Now, there's a reason why we did it this way first. And that's because I need to substitute this into here. Okay? I can't substitute in a j hat into an equation with I hats. Okay? You can't multiply I hats and j hats together yet. We haven't learned that yet. And you can't do it for these types of problems anyway. Okay? So what we're going to do is we're going to substitute this in for here. Okay? So I have negative mu sub k mg plus force on block by person is equal to ma. Now I'm going to solve for force on block by person. So force on block by person is equal to ma plus mu sub k mg. Okay? Now, giving it a direction, it's equal to ma plus mu sub k mg I hat. Okay, and so there you go. That's how you solve for the the applied force and the normal force. Usually you're going to need the normal force anytime you have friction. So if they say you have friction in the problem, think about it. You're probably going to have to solve for the normal force, especially if they give you the coefficient of friction. Okay, so this concludes example number 1 for 2D problems.